Hello everyone, what's up? Today I want to talk to you about some applications of the mean value theorem to some concepts in math. So we know that the main form to write the mean value theorem is to write it as a fraction. So usually you would write f of b, any function f evaluated at some point v, minus f of a is going to be divided by b minus a, and well, this will be equal to, remember, this is going to be the slope of the secant line between b and a. And we know this will be equal to some point on the x-axis, and we use that point c to evaluate the derivative for the function f, okay? So this is usually how you would write the mean value theorem. Now, of course, you can rewrite this equation by multiplying both sides by b minus a, okay? So if you do that, you would get the following. You would get f of b minus f of a is going to be equal to f prime evaluated at c times b minus a, okay? So now this is another way in which you can write the mean value theorem. And of course, there are some conditions. So well, there's an inequality that a, b, and c must satisfy. And we know that inequality will be a must be less than c, and also c must be less than b, okay? So basically we have an interval from a to b, and c must be inside that interval, okay? So now this is the second equation that I want to discuss. And basically, if you try to analyze this equation, well, you can prove many interesting facts about functions. So for instance, there is, I would say, we can probably call it a lemma in math and in calculus more specifically, and that is, if you have any function f prime, and if f prime is positive, so f prime is greater than 0, then we say that f increases, okay? This is a statement that usually you take just for granted and you don't really give it too much thought because it makes sense and it's very intuitive. But actually, you can use the mean value theorem to prove this statement right here. If f prime is positive, then f must increase, okay? So let me show you how you can do that. So if we analyze this equation, we can see that if f prime is positive and we know b is greater than a, that means that this factor right here will give us a positive amount, and f prime we know is positive. So this is going to be positive times positive. And if we get positive times positive, well, that means that this subtraction must also yield a positive quantity, okay? Now, the only way in which a subtraction, if you have, just two numbers, m minus n, you could say you have those two numbers, m and n, the only way those two can give you a positive amount, if you subtract them, is if m is greater than n. In this case, if f of b, f evaluated at v, is greater than fa, okay? Now, if we know that this must yield a positive quantity, we can write the inequality, we can write this following inequality. So you can write that f evaluated at b must be greater than f evaluated at a, okay? And we know this is true for b greater than a, okay? And now this inequality right here, well, these two inequalities coupled is what we call the definition of an increasing function, okay? Usually the definition of an increasing function is the same function evaluated at two different points, one greater than the other. And if this is true, if you can evaluate the function at two different points, one point being greater than the other, and it turns out that the function is greater at one of those points, we say that f increases, okay? And well, we can only do that, we can only prove this fact in a more rigorous way by using the mean value theorem, okay? And relating these two factors. B is greater than A based on the initial condition, so this will be positive and this will also be positive. And that means that f of b, f evaluated at b, must be greater than fa, okay? Now you can do a very similar analysis to what I just did here by trying to find, well, what happens if f prime is negative. So what if we say that f prime is less than 0? Usually we say that f decreases, okay? So we have that f decreases. Now you can also prove this in a very interesting way. So you can once again analyze this equation. If f prime is negative, then, well, we know this quantity will be positive, but we will get in the right hand side of the equation, we will get a negative value, okay? Because we have negative times positive, and this will be negative. So if we get negative on this side, that means that this subtraction must also give us a negative number, okay? And the only way these two guys can yield a negative amount is if fa is greater than fb, okay? So that means that we can write the inequality, well, fa So I should write this. So yeah, let me move this. So you already know I'm not gonna write b greater than a. You already know that condition. So I'm just gonna erase it from here so that I can write each inequality in front of its corresponding statement. So we know that, well, based on the right hand side of the equation, we'll get a negative amount, and that means that FA must be greater than FB. Okay. So we also say here that, well, FA must be greater than FB. Okay. So this inequality shows that the greater the x value, the greater the input of f is, well, the greater the output, the smaller the output of f will be, okay? Because remember, b is greater than a, so the greater the input of this function is, well, you're gonna get a smaller value as the output, okay? And so you get this inequality right here. And you could also do the same thing for constant functions. So usually when we say that we have f prime is equal to 0, we say that f is constant, okay? F remains constant. And once again, you can use the mean value theorem to explain this fact in a more rigorous way. If f prime is equal to 0, you don't really care what you get you don't really care what the result of b minus a is, because, well, you're going to multiply by 0, so you're going to get 0 on the right-hand side of the equation. And on the left-hand side, the only way you can possibly get 0, if you got 0 on the right side, you can only get 0 if f evaluated at b is equal to f evaluated at a, okay? And, well, that allows you to write the equation that f evaluated at b must be equal to f evaluated at a, okay? So no matter what your input is in the interval v and a, well, at least these two endpoints will be equal, okay? It doesn't mean that the function is just a straight line, because remember, you could have, a function that, I think the word in English is wiggles, a function that goes up and down. And then at the endpoints, you have the same value. You could think of, a parabola. So in the middle of the interval, you don't have a constant, f prime will not be equal to 0, but in the endpoints, it will, okay? So you get that the endpoints for this interval must be equal, okay? And you can prove that by using the mean value theorem and seeing that the right-hand side of the equation will be 0, and that only happens if f evaluated at b is equal to f evaluated at a, okay? So this was just simply some analysis that I wanted to explain. I think it is pretty cool to see how, well, you've got the mean value theorem. This is the slope of a secant line from a to b, and this is just any point, this is just the derivative of f evaluated at any point c inside the interval from a to b, okay? And you can use this idea to justify many statements that are very common in calculus, such as these ones right here, okay? If f prime has a specific value, or is greater than a specific value, well, then we can infer some behavior for f, okay? And, here's just a little proof, or maybe not a rigorous proof, but, just some more intuition based on the mean value theorem of how this works, okay? So yeah, this is pretty cool. I hope that you enjoyed this video, you learned something, and see you in the following one. Bye.